Good morning and good afternoon, everyone. Welcome to our second session of the lunch break webinars organized by ISCOV together with our partners at AST Environmental in Kentucky, US. Today we are going to talk about a bit of an experience we have learned throughout the years about in-situ injections and different application techniques, methods, and other aspects to be considered. The agenda for today, we'll go through a little bit of a general introduction, some housekeeping, and then we'll start diving into the details of what we want to discuss today, which is a bit of best practices and design, some key facts, the parameters that we looked in terms of installation and application when we're out in the field, what you need to look into and make sure that you follow what site conditions are telling you, and the monitoring that we perform during and post the remediation, joined by some case studies and lesson learned. We will then try to leave, as always, as much space as possible for a question and answer session. As for the previous session, depending on the browser you're using, you may move your mouse cursors to the bottom of the screen or to the top of the screen. A pop-up bar will appear. There is a Q&A box right in the middle. You can click on that, submit your questions, and we will go through at the end of the presentation. So for those of you that may have not been able to join our first session, you can either scan the QR code here on the slide right now, or you can find the presentation on either AST or ISCOV web page in the webinar sections. When it comes to the upcoming events, we have planned a third session, which will cover case studies related to hydrocarbon sites and again, covering the whole spectrum of design, application, and post-monitoring data, and sort of, again, share lessons learned and results from many years of application. This will be planned for May 21st, again at 12 o'clock lunchtime. When it comes to upcoming events in the recent future, both ISCOV and AST, as a part of the RPI group, will be present in Karlstad at the Rena Remark event. This will be next week. We will follow then the week after Mutku Days in Helsinki, where we will have a number of presentations, and we have been invited then to present both on the in-situ application methodology and something about PFAS treatment in Norrköping in Sweden on the 7th of May. About who's presenting to you today regarding these techniques and different application solution. Myself, Giorgio Ceriani from ISCOV. I've been now for more than 15 years involved with soil and groundwater remediation. Been able to sort of cover multiple projects, both on the mechanical side, so multi-phase extraction, soil vapor extraction, and similar type of large installations, and then move to bioremediation, which has been sort of my main focus for the last 10 years or so. I take now the opportunity to let the chair to Mike Mazaris from AST. Welcome, Mike. The panel is yours.
Thanks, Giorgio. Can you hear me okay?
Yes.
Okay, great. Good afternoon, everyone. As Giorgio mentioned, based in the US, based in Denver, actually catching a flight tonight to come over to come to Europe for the event next week that Giorgio mentioned. I've been in the environmental industry for this will be my 24th year, with most of my experience being on the bio side, as well as on the chemical oxidation, chemical reduction side. I would say for the last 20 years or so, I've been focused on injection of various remedial amendments, and I've worked on projects here in the US, Europe, as well as Australia. Next slide, Giorgio. Okay, so this first section here just sort of sets the stage for the rest of the presentation, and sort of just builds on that 20 years that I mentioned of putting various reagents, liquids, and slurries into the ground, and we'll get into the differences between those two here on the next slide. But just some general design observations. Spending time in the field, and you see what I would say proper designs, and then you see some inadequate designs for various reasons. And so I think first off, it all ties in with total mass, and that this first bullet here, really the first point, ties into the first webinar that we did last month. It's really understanding total mass in your system and where that mass is located, right? So the groundwater piece of your total mass is the easier piece generally, and the saturated soil, the adsorbed component, is usually the tougher piece. And understanding where that is and what sort of geology you're dealing with, where that mass is, really critical in source zones, because here, that's where the bulk of the mass is. Obviously, that's what's going to keep feeding your down gradient flux. And so in your source zones that have low K zones, especially, you've got to really match your application technique and your equipment. So you're going to have to match your technology, your technique, your equipment, all with trying to target that mass. And so, for example, if you have a highly variable layered geology that's got silts and clays and interbedded sands, and if you put a long screen direct push tool or an injection well, maybe you're going to target the higher K zones, and it's difficult to diffuse reagents into these lower K zones. If it's shallow enough, soil mixing is always going to be your best application for any technology, because you cannot get better contact than that. So that's generally going to be our recommendation for soil for shallow applications. And then your strategy, obviously, sort of, you have a point of divergence here where you look at source treatment versus permeable reactive barriers. So you're going to have different paths depending on which one you're looking at. And a lot of our sites that we do, that Giorgio will show you here shortly, have a combination of these. So you have a source area, then you have a down gradient PRB. But these are all, and they might deploy different technologies, and they usually do. But number one, what's your reagent longevity? Because we've got things like hydrogen peroxide or other oxidants that are on the days to weeks end of the scale. And then you've got things like zero valent iron-based chemistries, which can last potentially decades. So understanding that longevity and your flux too, is to help understand the advective component, is going to be really critical. And that ties in with your dosing. We'll get into here in a minute. Especially with liquids, you can dose those a little differently, but that dosing is all going to obviously tie in with that first bullet, right? So you understanding your total mass. And then lastly, really the point of this entire webinar is trying to ensure that you get contact between your reagent and the chemical of concern. And then lastly, making sure that your pressure, flow rate, spacing, volumes, those all need to match the reagent and the geology, and we'll kind of get that. We'll get into that a little bit more here on this next slide. So thank you, Giorgio. Excuse me. So, reagents are going to fall generally into two categories. You're going to have liquids and slurries. We'll kind of go through the differences between the two. So liquids, your chemical oxidants, your colloidal size technologies, emulsified vegetable oils, and would fall into the liquid category. On the slurry side, your larger grain size activated carbon that is not colloidal. So things like powdered carbon, granular size carbon, zero valent iron kind of fall into that category. And so you can see here, we've sort of listed differences. Generally, your liquids are going to be applied under low pressure, low flow conditions, and you're just trying to, what I say is fill the bathtub, right? Trying to fill that pore space with whatever your liquid is. Slurries are a little different. They're generally going to be lower volume injected, but higher flow rates, higher pressures. Obviously, you're trying to push a solid into a solid matrix, right? So we've got to apply more energy. For liquids, usually that could be done with direct push. You see a typical liquid injection direct push tool down there at the bottom. That can be anywhere from 0.3 to 1.5 meters. Or you could use injection wells. Those generally, I don't recommend injection wells being any longer than 3 meters. The smaller, the better if you are going to use that application technique. But when it comes to slurries, you really are limited to DPT and DPT jet injection that you see the picture down there on the lower right. And that's really, again, we're just like a pressure washer. We're trying to force that slurry into layers in the subsurface. And it is difficult to target lower K zones, as I mentioned before, with liquids using these low pressure, low flow techniques. Slurries, you can really now, your strategy and your application can change, but you can inject into both low K and high K aquifers with slurries, but your variables are going to change. So your spacing, volume, injection tips. The injection tip is going to drive your injection velocity. And so we can manipulate that as well. So your strategies change, but we do have the ability to inject slurries into both. Next slide, please. And so just one sort of last wrap-up slide here. So these are really the main techniques that we use to get reagents in the ground. Direct push that we've already covered. That's your overburden clays through gravels. And again, as I just mentioned, you can apply slurries or liquids into sands, gravels, but when it comes to clays and silts, really that's sort of where slurries really have an advantage over liquids. Okay, and that's usually done. That's most of our projects are done using direct push. That pre-drill technique that you see there, that's really for sites that have direct push refusal but are not competent bedrock. And that's where we use sonic or augers to advance through that refusal zone. We backfill that with bentonite, and then we can re-drill that point with direct push. We've used that successfully in Europe as well as here in the US. And if it is competent bedrock, we have that is the system that we use here in the US, where we use straddle packers to isolate fractures to be able to inject the amendments. And then lastly, on the right, soil mixing. The project on the left, I believe, was a site in Finland. The one on the right is a project of mine that was in the eastern US, where, again, if it's shallow enough and you have the access, this is really the best way to apply any amendment. But at the end of the day, we don't have that access at all sites, obviously, so we end up having to default back to injection techniques. Giorgio, I think you're up.
Thank you, Mike. So continuing on from trying to set the stage of what we'll try to cover in the upcoming slides, we also have to look, as Mike was pointing out in the first slide, about the design, especially when it comes to source versus barrier. So when we look at dosing and longevity, those are critical things that we have to keep in mind. So will the material be something that it's going to stay in place, or is it something that will dissolve and flow together with the water or travel with the water for whatever reason? How much material can you actually deploy in one event, and how does it fit with the contaminant mass distribution that we have observed and learned by doing high resolution design? Can we degrade over time that whole contaminant mass? Will there be something that will be left over? How does it match with the overall project criteria? And then look at all the sort of limitations that can be present at a site. So can I get a good coverage of where my contaminant is located? How is the geology looking like? Do I have enough space to install a PRB if that's needed? Would I have a risk that something will stall my degradation process or treatment process, and there could be a risk for a rollover effect? So all those things have to be taken into account. Here I used a few visual aids from a site that we have where we have done a remedial design last year, where we have to look at both environmental and business objectives combined. So here you have an active retail station where a large source mass had been found compared to the initial estimates. When we look though at the drivers for the remediation and from the authorities, there is actually a downstream well that is clearly impacted by benzene and MTBE, and that actual residual mass of benzene and MTBE is present more towards the site boundary in the southwest portion of the property. So when we look at the client needs, is that of course they would like to maintain the station operational, but at the same time make sure that things are done according to authority requirements. So the design that we provided, as we can see also from the cross section based on the soil contamination, is sufficient to perform a sort of source treatment on the residual mass present that we can cover without disrupting the sales operation, but at the same time already acting as a sort of barrier for the contaminant mass that will leach over time through that treatment zone. And then we have a diving groundwater that starts very shallow at the site and then drops for about 4, 5, 6 meters by the time it crosses the road. And that's where the PRB design comes in place. And that's where the target criteria become really important to be achieved, because that's sort of your last resource solution. So all those things have to be considered. So when we then move into the field application itself, what do we normally try to look for? Again, bound to the design is the grid spacing and the layout. So we generally recommend to work on a triangular grid pattern to achieve as the most homogeneous distribution as you can think of. The spacing is of course a function of how deep the contamination is, the type of lithology, geology at your site, and then look at the site constraints. So not always you'll be able to have a perfectly homogeneously triangular grid. You may have to go around some utilities, some, as we saw from the previous slide, a main road in between the site and the last permeable reactive barrier. And then also the technology selection. So is it a liquid amendment or a slurry amendment that we're trying to inject? And that will affect the spacing. What we know from experience is that the more you push your grid beyond, let's say, 2.5 meters, the more we start to be in sort of unknown territory, because now you start to push your luck in terms of distribution and where either a liquid amendment or a solid amendment will start to distribute in the formation. And again, when it comes to a PRB, let's think about what a PRB has to do. So it has to provide a long-term solution for the site, for the client, and for the authorities to have confidence that that solution will last for many years to come. So again, there, the spacing, it becomes even more critical, because you have to ensure that the reagent installed will cover the entire flux zone, will ensure that longevity, and most importantly, a sufficient space where the contaminant mass flux has sufficient contact time with the reagent installed, being a slurry, being a liquid.
Giorgio,
Yes.
do you mind going back to that slide? I just want to make one more comment.
Yeah.
So, another observation that I would make is that when you get designs, so designs come from different places. So some designs are derived internally within the various consulting firms that we work with. Other designs are provided by the vendors themselves that provide those chemicals. And then there's a third party in general that's going to be applying the technology. And so I would just make sure that we can play with safety factors when it comes to the reagent dosing, right? Based on the information that we have in the conceptual site model. But I would say this is where projects mainly fail, is on the contact end of things. And what I've seen is that you just have these very large spacings, and they're not realistic. And because, as you imagine, as your injection point spacing increases, the amount of volume you have to inject increases, obviously. And so, especially when you're on developed sites, which most sites we work on are, then now you have a much higher probability of encountering some sort of ground disturbance, whether that's an old soil boring, whether that's a trench, some sort of service line, excavations, and any slight variation in that hydraulic conductivity is going to force that fluid into that disturbed soil. And so my recommendation to everyone here is to be conservative with your spacing and have it as tight as you can. If that includes some extra time in the field, again, I think that's going to give you a much higher probability of success. Thanks,
Thanks,
Giorgio.
Mike. Yeah, I was gonna leave you the word on also the volumes and exit velocity if you like to
Right. So
share some
yeah,
thoughts. Yeah.
yeah. So when it comes to liquids, you can really apply these in two different ways. You've got your high volume, high percentage pore volume at typically typically at a lower dosage. This relies less on advection dispersion, but you spend more time in the field pumping, right? And so there's a trade-off, obviously, with the low pore volume, which is going to be a higher dosage. Now you're relying on advection dispersion to move your material out. And so that's going to depend on the hydraulics of your site, having a good handle on your transmissive zones, which are hydraulic conductivity, your gradient, all of those, as to which one of those is going to be which one of those is going to be more appropriate. Exit velocity really doesn't. I mentioned exit velocity earlier, and it's really critical for slurries as it applies to liquids. You're really looking at low pressure. You could be injecting under 1 bar, say, and so the exit velocity is going to be very low. And so that's another reason why you really can't get into these lower K zones. There's also an aspect of the system itself too, where if you go out and if you're going to be injecting liquids, go to the field with a couple different pumping options, because if you go out with something very low pressure, low flow, and you cannot get it into the formation, now you're maxing out your pump. That can lead to equipment damages. There's also safety concerns too now, especially with, say, things like chemical oxidants. And we'll come back to exit velocity here in a minute. And I think it applies more to the slurry end of things. But as for how those contrast with liquids, these are going to be injected under higher energy, right? Higher velocity. And that makes sense, right? As I mentioned, we're trying to push a solid into a solid. The volumes are going to be relatively low. So we get the question often, are we going to be pushing my contamination outside of my treatment zone? Which is a question really for both liquids and slurries. But on the slurry side of things, those are all going to be relatively low volume. And if you work out the math, if you do the math on how much solid you're putting into a given treatment area, it's usually pretty low. It's going to be low single digits. And as in both, you really want to assess that volume, and that volume may change. Again, your volume may change depending on where you are on site, depending on the geology and the conceptual site model again. And so you have to, as that third bullet mentions, you may have to just have some flexibility there. And your injection point spacing, just to go back just to that previous slide that we just covered about, that your spacing may change as well. So for example, if I'm working at a petroleum station, and if you're working around, say, the UST cavity, your injection point spacing might be tighter, because again, we don't want to be pushing our fluid into that cavity. But the rest of the site, we might be able to have a larger spacing. So that may be modified, and that goes really for both of these techniques. But as it pertains to exit velocity, this is something that with slurries you need to pay a lot of attention to, because you can manipulate the velocity depending on. So if you have a static flow rate, how we calculate exit velocity is you've got your flow rate, you look at your injection downhole tip. If you remember, it had all of your injection ports were in one plane. if you add up the area of those ports, divide your flow rate by that area, you get your exit velocity. And so we try and match up that velocity with the geology. And so, for example, it's somewhat counterintuitive. You have to have a higher exit velocity when you are in something like fine or medium coarse sand, because the sand wants to really filter out the solids. And so you actually have to put more energy into a sand than you do a clay whenever you're dealing with slurries, which is somewhat counterintuitive. And obviously, from a safety aspect, you want to make sure that your equipment is designed to handle whatever your maximum pump pressure is, plus a safety factor. Okay. And as I mentioned, that last bullet, this is really the key to getting distribution in, say, finer grain and coarse grain, is really being able to manipulate that exit velocity, and again, come out to the site with options, especially in your pilot testing phase, where you have multiple injection tips with different port size, different numbers of ports, and with different diameters, so that you can play with that exit velocity to see what's going to be optimal for your site.
Thanks, Mike. Well, linking up to what we just discussed about spacing, exit velocity, volumes, we then look at what the pressure signatures are. So when we focus on the slurry part, that is pretty much our trademark, we have seen, and we can follow distribution by performing, for example, validatory corings. And here are some examples that kind of match what we have tried to explain. So when it comes to sands, you are gonna work with a much higher volume and velocity, exit velocity, which leads to a more turbulent mixing of the formation. So the picture that is shown on the left end of the slide shows an homogeneous distribution of a powdered activated carbon slurry within a sandy formation, versus when we go into clays, where you need to create a small fracture, and that is where the equipment really kicks in, where you can build up some of your back pressure to distribute that slurry out in the formation. And the pictures below actually show a nice transition zone from a gravelly sandy formation to a hard clay formation, where we can see the distribution being more homogeneous on the left end in the sands and gravels, whereas in the tight clay formation, we have a more tree root type of distribution, and that shows how the materials try to propagate in soils. And there again, another nice core of a clay formation, where you can see a nice perpendicular cut within the core of how the slurry is distributed. Now, when we look at another critical factor that we try to make sure we cover nicely in the field, is how we keep track of our injection. So recording of the information while injecting is critical. The more we look at the projects executed over the years, it becomes obvious that, especially when you deal, for example, with redevelopers, you want to know exactly where you have done some remediation in situ application, so that whatever happens in the future to that site, you can trace back where you have been, you can understand what your data from groundwater and soil validation is telling you. And pretty much we are able to use the tools that we have also on the software side to record all that information, create a sort of as-built report for the client, so that at any given time in the future, we can go back, look at what has been done, and make sure that all information are stored accordingly. And this also fits pretty nicely with sites that may undergo, for example, a sales transaction, so that whenever a new buyer comes in, if you have used, for example, a slurry which has stayed in place over time, and the buyer wants to make sure that that material is still there, you could easily trace that back by doing validatory coring and trace that information for sales purposes. When we look at the monitoring part during the injection, some of the little things that we look at, and it's not so small, but they are important. One is definitely the pressure. Just when we inject, I think that's our baseline value that tells us how things are going. So again, if we know that a site is mostly clay based, and I see my pressure not really doing that little break curve that we have seen in the graph before, it kind of starts to raise a question. Am I getting good distribution? Is there something that I'm not able to obtain down at the nozzle with my equipment? Am I capable or not to pushing the material where I want to? And when I work in sands, if I see, for example, a pressure constantly rising during the injection period, that would also sort of raise an alarm. And that's why our teams are always only trained personnel that know how to follow specific procedures. We don't rush in doing things, but we try to make sure that what costs more, which is the material, you only have one chance when you're out in the field to put it right in the ground. And so we use that initial baseline with the pressure reading to give us an understanding of how things are going. On the groundwater side of things, there are little tricks that could be used in the field by, for example, installing pressure transducers in the wells, or performing just manual groundwater gauging, or stop for a day, do a few confirmatory borings as well to just check presence of the product. And that allows you to go through the installation period with a little bit more confidence, so that by the time you're done with the installation, you already have a sense of what you have done and what you could expect out of your future groundwater data. So the message we want to send out is pretty much that sometimes we hear like installers or vendors just saying, it's something easy to install because it's something liquid, it will flow easily through your formation, it distributes easily in sand, things like that. Just because you're told that it's easy to inject, it doesn't mean that you can trust the outcome. So installation is what we based our sort of guarantee of our results onto. And another key aspect that we always see in the field that sometimes happens, sometimes not, it's daylighting, and we have learned to handle it, and we know that eventually it's going to happen, but it's not always a bad thing because it gives you an idea. Maybe you're actually getting good indication of good distribution just by a few daylighting events. But then again, you want to think at the big picture. So when we look at sites where we are performing 300 injection point, it's not one injection point that gives you the guarantee that your results are going to come, but it's the overall injections of all the 300 points. So we like to make sure that the CSM is always in our focus, in our mind, so that we try to evaluate how the daylighting is occurring. Is it an instantaneous daylighting versus a delayed daylighting? Because that will tell you a lot whether it's possibly an open borel versus something more natural. So what we try to do is to think, how can we adjust injection volume, the spacing, the sequencing of the intervals? Do we have to skip some intervals? But again, we need to know where the mass is so that we can always try to target that mass of contamination as good as it gets. And that's the experience we have from over hundreds of sites performed, where, for example, in some of the cases shown here, personally, I've been removing a 15-meter long well from an open borel. As soon as I saw some instantaneous daylighting occurring, I thought something is wrong here. And the drillers that came at the very early days at the site never put sand and bentonite around the well. What can you expect when you inject fluids in the area? Instantaneous daylighting. Similarly, you can find in clay formation open borels to, for example, 10 meter, which have not been sealed properly. And again, when you create fractures and you find that contact with those open borels, there's only one thing that can happen. So in short, we try to make sure every time we jump into a project that we have all the information about historical borings and where the site has been drilled, so that in case of future injections, we can always go back and trace location, which may become troublesome. And to look at the post-monitoring, just to wrap up the presentation and leave space for questions, a few cases that kind of show where we have got with installation of solid amendments, so slurries. In this case, it's CAT 100 technologies, which is based on granulated activated carbon. But we see a site where during the design phase, we had encountered large amounts of DNAPL. The picture shows clearly PCE popping out of the clays. And post-injections, we have seen the trends. These are data collected by the consultant in charge, where we saw the DNAPL present reducing over time. The removal of the DNAPL went from few liters at the very beginning to no more DNAPL being available for removal. And based on soil validation, we were able to define and estimate a 40 to 50% reduction in soil mass within a period of about 4 years post-installation. We also installed at this specific site a twin well next to the original DNAPL well, where we could see PCE reduction in groundwater to a level of 98%. And most importantly, downstream of that specific DNAPL area, we had a good proof of evidence that mass was not escaping, but actually biologically degrading in the source area, as we can see from the graph in the bottom right, where the concentrations of all the chlorinated compounds have been kept in check now for the past 5 years. And these are all data collected by the consultant. And again, as a line of evidence, in this case, as I mentioned, we have injected a solid amendment slurry, which has a component as a slow release electron donor. And the proof of concept of that donor releasing in groundwater is provided by the generation of ethylene, which was not at all present at the site before the remediation, and then just slowly building up with the plume. And thanks to the presence of naturally occurring bacteria that were luckily available at the site, we were able to degrade PCE naturally from very high concentration. At the site boundary, we had approximately 100,000 microgram liter to now less than a few hundreds microgram liter within a short period of time. On the LNAPL side, another interesting case study that sort of summarizes the whole concept of design, constraints at the site, business and environmental objectives. Here we had a gas station where we did a large remedial design, followed by, as we can see, a surgical injection plan, which was divided in a total of 17 sub-areas, each sub-area with a different dosing profile, layout in terms of criteria that were to be achieved, because we had performance, it was a performance-based contract. But most importantly, we had to keep the station alive. The client didn't want to cease sales activity. And you can see that you have to sort of come up with the design that, yes, it could be seen as a triangular grid spacing, but then think of an active gas station, fuel lines, USTs, oil water separators, you name it. So you can see how the distribution then of the points have to be adjusted to site specific condition. Here we completed a remediation with 287 injection points. We injected BOS 200, which is a powdered activated carbon based slurry. And the results, again, were made quite clear by validation events that were actually asked by the client on soil data, for example. We started with the blue line, which shows the pre-treatment concentration, followed by 2 validation events performed 3 years after the first pilot test, and then 2 years after the full-scale event. And we can see the reduction in soil concentration just by looking at the soil data. This well, by the time the site was granted no further action, reached non-detect concentration for benzene. 150 centimeter of LNAPL that were observed pre-pilot test were not observed after the full-scale event ever since. Mike, would you like to also comment on one of your cases?
Sure, I'll keep this brief so we can leave time for question and answer session. But these are 2 sites that I've worked on here in the U.S. that use both slurries and liquids, and just to compare the 2. So the one on the left was a gas station outside of New York City where multiple rounds of chemical oxidation. So before day 0 that you see on the graph on the left, they had 5 applications of a particular chemical oxidant. They came out several years later and attempted another chemical oxidant. And then we got involved where you see the technology C line came out and did a high density soil sampling, identified where the mass was. The mass was bleeding out underneath a very busy road. It really couldn't be accessed. And so we created a PRB along that line and then treated the site and using that Boss 200 technology that Giorgio had mentioned, and then within a few years, we're able to be granted a no further action on the site. The one on the right is another petroleum site that had 2 rounds of a colloidal carbon product applied, as well as a 3rd round of chemical oxidation. This was in a very tight glacial till. This is in Canada, and so you can see there a lot of variability in the BTEX and your PHC concentrations. Again, fast forward a little bit in time to the blue box, shaded box to the right. We came out, did a high density sampling, and determined there was just too much mass, and they didn't put enough product in the ground, really. And they had 1 row of injection points for the PRB. We typically recommend multiple rows. They really didn't get enough material in. They didn't really have enough vertical intervals injected, and they applied under low pressure, low flow in that tight glacial till, and just could not get contact. And so we came out with after the RDC, we did 1 application of the same technology that was used there on the left, and you can see the results. And we were that data actually that is only shown until August of 2019 actually has been. I had a discussion with the client last month, and that data has continued to stay down. So I know we're about 40 minutes in, so I guess you can put any questions you have into the Q&A box, and we're more than happy to answer those for you. Thank you for your time today.
Thank you, Mike, for the help today. Let's see if some questions start to come in.
So I guess, Giorgio, I'll just kind of kick things off, and just a question again that we get often. I'll let you answer it, because I'm used to using imperial units. You can
Yes.
relate the metric for me, but regarding the flow rates, really didn't give specific flow rates. Maybe talk a little bit about the sort of flow rate ranges and sort of the pressure ranges that you see on your sites.
So if we look at, for example, clay formation, and starting from, let's say, a tight grid, which we normally recommend being, if we treat, let's say, shallow formation from 1 to 3, 4 meter, we would work on maybe 1.5 meter grid spacing. We would recommend not exceeding 30 to 40 liters volumes. The pressures that we normally see as a dissipation on soil and clay formation is nothing that goes beyond anywhere between 2-5 bar. Maybe Copenhagen area, where the clay is pretty tight, we may see some spikes at 10 bar in this sort of break pressure. As you move downwards in the formation, you start to enlarge your spacing grid to 2.3 meter. You start to move your volumes, your shot volumes, to maybe 60, 80 liter, 90 liter at the max in silty clay formations. Shift that to sands. What we look into is, again, the grid spacing, similar grid spacing. All we do is beef up a bit the volume to say, so where we start at 40 liters per shot in the shallow treatment zones, we may go to 60 liter shots. And if you go deeper, you may reach 100 liter, 120 liter per shot. The pressure signature in sands, as we discussed, it's not something like the clay that you need to see a break pressure. You want to see a constant and even pressure. So what we normally do at the start of each project, we test our system in an empty drum, so that we can see our baseline pressure, which is the energy that your system is building up to carry your slurry from the mixing tank over to the injection nozzle and out of the 5-6 holes that we have on the nozzle. If you take that baseline, now you know when you inject what you are seeing in the formation. So let's say, for example, your baseline pressure is 25 bar. Now you start injecting and you start to see 30 bar on your gauge. It means, okay, that's the formation back pressure that it's working on the system. And from there, we can take decisions.
Well, it looks like we've got a question on the one slide that you mentioned that had that showed the ethylene,
Yeah,
and the question is about the microbiological, because you had mentioned that the bacteria were present and what sort of microbiological analysis was done.
yeah,
I can handle that one. So, it's,
yeah,
I think, especially on chlorinated sites, as part of the RDC process or part of that upfront CSM development, I always recommend to have an understanding of, what sort of, whether your key dechlorinators are either present or not present. And on that particular site, the halicoides was present, I think, in most of the wells outside of that DNAPL area. And
correct.
so even though that, say, particular technology that you used does not include the halicoides, that we're able to, with the addition of the electron donor, able to stimulate um, those bacteria as well. And I think that's kind of a good general comment as well. When you're using microbiology uh, for a bioremediation strategy, that you often will have what I call a halo effect of if you're using something like activated carbon, you have what's going on within the carbon, the bacteria that if you add bacteria to that, which is we feel like is really a key piece. If you're going to add activated carbon, the bacteria are going to sorb to the carbon. That's where the bacteria are going to be adsorbed onto. But you're also adding electron acceptors or electron donors, depending on whether you're working on hydrocarbon or chlorinated sites, and those don't adsorb onto the activated carbon, and those are going to diffuse and advect, and so you're going to have what I call a halo effect of enhancing your natural degradation outside of say the activated carbon. And so I would recommend petroleum hydrocarbon sites. We don't typically do it. If you look at your historic data and you have electron acceptors present, so you have things like oxygen or say sulfate present, iron maybe, and if you're not seeing degradation naturally, then that may be a trigger to do some, look and see what you can do, like next gen sequencing, which is sort of the has all the bells and whistles. It tells you exactly what's there. It tells you all the bacteria that are present, as well as so you can find out. You can look at specifically as to whether or not you have methanogens or sulfate reducers, for example. On the chlorinated side, obviously, we already covered that, sort of the same thing, looking at functional genes. So if you have, say, vinyl chloride degrading organisms, do they have the functional genes present to be able to degrade things like, say, vinyl chloride? And I guess one last question was about that pre-drill technique. I don't know, Georgia, if you just want to go through that real quick before we go ahead and wrap up, and maybe just give an example of where that's been used in Europe.
Yeah, at least from our side, we have used that in dry sands formation. So we have been encountering sites where groundwater had been was present maybe 10, 15 meters below surface, and the upper soil was purely just dry sands. When again, working with direct push, dry sands can become a limitation because of the friction that creates around the rods. So the best way forward there was to actually use a rotary rotopercussion drilling machine, pre-drill down to the target depth of the injection, which that's some specific sites we have been, that specific site I was talking about was 18, 19 meter depth, backfill the holes with bentonite, and then go through like butter pretty much with the direct push equipment. And again, when deploying a solid slurry as it was for that site, then again the equipment, injection equipment came into account, because then you were able to break through that bentonite pack very easily and then dissipate the product within the formation as needed. So that's how we have learned. We don't want to steal more of your time, since we try to keep this within 45 minutes. You see both mine and Mike email addresses in this slide on the screen now. If you have any question, and feel free to contact us. If you are based in Sweden or Finland, then we'll participate to the upcoming events at Mutko, and Reinar and Mark will be happy to answer your questions. And we hope that you make it to our next event on May 21st. We'll go through some of these topics that we discussed today, but a bit more in detail with regards to specific cases. Thank you so much, everyone, and have a good rest of the day.